Hello, Professor. My name is Harrison Hopkins with Kennesaw State University's AI class of summer 2019, and this is our Project 3, the project that requires us to implement a perceptron and a multi-layer feed-forward back-propagation algorithm, or AN. This was by far one of the harder projects that we had to work on this class. It took a lot of noodling, and some of it is still a little off, I'd say, but it works for the most part. So, for this video, we're going to start off by showing off the perceptron. I'm going to start by playing this, and as usual, I'm using Unity as my developer because it offers great GUI elements as well as a good program handler. So by hitting play, it's going to load me with all of these. These are the 4 elements, so you can change them between black and white. So first things first is I'm going to click Set Default Weights, and you're going to see a set of weights appear above all of these. So default weights is my more reliable class. It sets each of them to an evenly balanced weight, and now you can hit test start and it'll tell me if it's bright or dark. Obviously it's bright now because all of these are white. Still bright. Now it's dark. So the program goes back and forth telling you which is the predominant selection. Now we can turn off all of these and set random weights, and it will select random numbers for each of these, and they can be applied in. So still dark, now bright. And it'll change varying on how many times you click set random weights. Each of the numbers can be very different. So to get into the coding of that, we're going to jump over to Visual Studios. This is my perceptron code. As per usual, we have the top here, where I laid out a bunch of public arrays, which contain my buttons and text and the images that change colors to create the GUI. And then I have a couple private arrays and some other things. The bias, which is only really used when utilizing the random weight assigner. Current weights, which helps take in all of the weights so I can display them later, and it keeps track of them for the program. The learning rate, which is how it's going to learn over time about understanding the information it's passed, and then another array for the selected pixels, which again is just tracking information for it to work with. So in the start, essentially all we're doing is initializing the weights and the learning rate, which is not used unless the randomizer is going, and assigning all of the pixels to the standard color, which is white. So again, here, the current weight, the learning rate, pixels, and then we have a for loop that goes through, takes every single pixel and sets it equal to 1, which is the standard. Down here in base perceptron, this is setting the base weight to 0.25 on all components. So as you saw in the code, when I hit set base weight, this is where it goes through, takes all of the current weights within the weight array and sets them to 0.25 and iterates through, as well as changing the string settings to understand for displaying the 0.25 for each weight. So, and then down here it sets the bias to 0 because it's not very well utilized without the randomization. And the randomization only sometimes works. I was having a lot of trouble ironing out some of the issues that it had perceiving the value based on the different numbers, because sometimes it would choose left or right, not depending on what the number was. So, this is the fill perceptron. So, it goes through and fills the entire thing with random weights. That's what this area is about. Like I said, it only works sometimes, but it fills them with a number between -1 and 1 to help it decide dark or bright, and then pumps out the weights onto a string to display the information. So it also sets the current bias equal to a random integer between -1 and 1, as it does up here with the current weight, and it starts the train perceptron run, which is where we're training it to do things. So train perceptron, like I just mentioned, it's training the perceptron using 16 different cases. So these are the standard cases, all 16 of them for a 4 digits being 0 and 1, and their potential outcomes. And then you move down here and you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way through 16, and it has each of the cases, and it'll iterate through this with the for loop 1,000 times. So it'll use this to help train and generate a base knowledge of what it should be expecting out of each of these to help it decide bright or dark. So we'll collapse that. And then here we have the update weights area. Now again, this is only used if I'm utilizing the random, which is fill perceptron, if I'm utilizing random numbers. But what it does is it checks the weight each time something is off and multiplies it by the expected outcome minus the output. So it's essentially checking to see how right or wrong it was based on the comparison made, like I said, by multiplying the expected minus the output. So it goes through and does this for every single one of the weights that is assigned to it, and the colors as it is run. And with the training, after training the perceptron, it hopefully knows enough about how these things would usually turn out, or what the expected result is, to guess closely enough that it is correct in understanding bright or dark. Next up, we have the training function, which again only used if random assignment is working, but this will multiply each input by the weight and then add the bias. So again, it works all the way through. You can see that some of this I had to cut out because I was doing a lot of playing with it. This is very difficult to understand. But it goes through and takes the perceptron's current value, the current weight, and then adds it with essentially all the positions of it. So 0, 1, 2, and 3, that's each of the different colored blocks. And then it updates the weight based on the expected 1, which is white, and the perceptron, and then -1, which is dark, and then perceptron. Then we move on to function, the method that I wrote that adds all of the weights times the input. So again, you can see a lot of random checked out areas where I was playing with the math to try to make it work a little more consistently. But again, this takes 0, 1, 2, and 3. It takes all of the potential colors, and it checks them, and then it will, with this if-else statement, it decides whether or not it is yellow, which is my bright color, as you saw before, and then will display bright. And if it's not yellow, it will determine that it is actually black, and then the dark colors, and it'll display a black cube and the word dark. And then these two things at the bottom here just update my text. So if it's bright, it says bright. If it's dark, it says dark. And then finally, we have the change color, which is just a simple method I wrote to work with the buttons. So this is, if you click on one of the buttons, it will change the color to white. If you click the button again, it'll change the color to black. So that is essentially how the perceptron works. A lot of that is based off of how the AND works, or teaching the neural network on the other code works. But it was still quite a doozy to write. I've never written anything like this before, so it was very hard to understand how to make the random integers work, but I believe I got it close enough. Again, it understands light and dark. So the next thing that we did was part 2, which is implementing a multi-layer feed-forward back-propagation algorithm. That is a lot to say, and we call it AND. So this is teaching a neural network to classify things. So what I have here in this scene is, again, I have 4 squares, each one of my 4 pixels, and as it loads, you can choose which one of these by clicking to make light or dark. So you can make any of them light or dark. So if I click test start, it'll understand that this is dark and state darkness and change my decider, the final result, to black. So then we'll get rid of some of them, and now it understands that it's bright. And you can run this test multiple times to figure out each result. So now we're going to dive into the code for that one back in Visual Studios. The first thing we're going to look at is the neural network code. Now, this was a lot of writing. This is a very, very complex algorithm that took a lot of time to understand, and even still, I feel like there are some things that I don't quite get about it. So I'm going to go through this as I possibly can. So the first thing here is organizing an integer array to hold information about the layers, and then an array made from the actual layer class that I wrote below to hold information from that. Oh, gee, not what I meant to hit. Then we start off with the neural network code int layer. So right here, this is where, because it's taking in an integer array called layer, but we also have an integer array of layer here. So I use this dot layer to make sure that it differentiates between the local layer and the global layer variables, because it's easier to name it that way instead of having a million different names, but I wanted to make sure that the program knew which layer I was referring to. Then we go down into this for loop, which goes through all of the length of the layer array and sets each one of them. Essentially, you're setting this layer, the global, equal to the local variable. So it's going through and making those hold the same information. Finally, layers, which is the one I made up here for the class array, it contains layer.length -1. So it has one less than the layer array that we worked with in the for loop right above. And then down below that, it takes each of the layers of layers, the class array, and sets it equal to a new class object, each one with layer of I, so used here, and then layer of I plus 1. So it sets it equal to the current layer and the next layer in each of its locations. So moving down, we move into the feedforward method. So feedforward is the method that essentially runs feedforward propagation and runs. This is the version that runs outside of the layer class, because there is another version that I had to put inside of the layer class that we'll see later, and it takes in an array of floats called inputs. So the first thing it does is takes the very first element in the layers class array and runs the feedforward method on it for inputs, which is again what is passed into this as a variable. And then it runs a for loop for the entire length of the class array layers. And for everyone, it sets I.feedforward to itself, or the variable before it, so layers of I minus 1, and then the outputs of that. So this was a lot of noodling, a lot of figuring it out, but essentially it iterates through each layer getting feedforward. That's why I wrote these notes down, so I can remember exactly what everything did. And then finally, it would return the class array of the output information for its the last one inside of the actual layers. So it'll take layers.length minus 1, which is the last element, or the one right before the last element, and then push out the outputs. So a lot of noodling, and we'll see feedforward again later inside of the actual layer method, but we're not there yet. My final method outside of the class layer is backprop. This again takes a array of float called expected, and it propagates through the visible layer. It backpropagates through the visible layer. So starts off with a for loop that runs through. It starts at 1 and runs through all of the layers, or the entire length of layers, which is again my class array that we established earlier. And then checks that if I, so whichever number it's on, is equal to layers.length minus 1, so the end of the layers array, then it'll backprop output. It'll take the backprop output of the expected, which is passed through as a parameter. Otherwise, layers.I, so whichever element we're on of layers based on the I up here, it'll take the backprop hidden, so it'll check the hidden backpropagation of layers of I plus 1, so the next area in layers, dot gamma, and the next variable in the layers array dot weight. So it's essentially taking the gamma and the weight of the next variable and getting that information. Then we move on to the last for loop in backprop, and what it does is, again, I equals 0. It runs through the entire array of layers based on the class, and takes the variable I and updates the weight for every single one of those by running the update weights class or method that we will see later. Now we're on to the public class layer, which is the class that I wrote to help handle the tracking of the layers. First two things I do are create the integers for number of inputs and number of outputs, just for tracking the neurons from the previous layer check for input and output. And then establish a large number of arrays that will serve a bunch of various purposes. So there's 4 standard arrays, 2 2D arrays, or 4 1D arrays, 2 2D arrays, and they're handling outputs, inputs, weights, the weights delta, gamma, and the error, as well as getting a randomizer properly inserted into here so that I can create random numbers later as required for the numbers between -1 and 1, as was done in the perceptron. So just weight handling. So moving on to the first section, which is it takes public layer, so it's running layer, taking in an integer, the number of outputs, and the integer number of inputs, which we established right up here. So, and again, to help separate the local variable version and the global variable, I used this dot, so it keeps the number of inputs and outputs, both global and local, separate. But I do set them equal to each other because I do want that information inside of this method. So then down here, we are establishing each one of the arrays we set above, and it's mostly going to be the number of outputs or inputs. So outputs is equal to outputs, inputs to inputs. The weight is equal to outputs and inputs, as well as the weights delta, and then the gamma and error are both based on outputs. And then we're just we're running the initialize weights method, which is directly below. So the initialize weights method initializes the weights for the neural network code, which is this whole thing. So what it does is it uses nested for looping, so an int I, int j, and it runs through the entire number of outputs and then inputs, and then checks weight for each one of those locations. So our array weights for each location, which you can see above, is set to the number of inputs and outputs, and it sets that to, and this is where I had to use some math. So I'm float casting unity engine.random range between 0 and 1 minus -5. So this is setting the weight equal to a float between 0 and 1 minus the -5. So that's how it's going to establish the weight of every single one of the sections in the actual weights array. So then we move on to feedforward. So this is what propagates forward through all the information inside of the neural. I keep wanting to call it a perceptron, the neural network. So again, it takes in a array of floats called inputs, and I'm using this .inputs to differentiate between the global variable and the local variable, but I am setting them equal to each other so that I have that information inside of my method. With this for loop, we're going through the entire number of outputs one at a time, and we're setting the outputs of I equal to 0, so we're essentially resetting the outputs as we run through this every time. And then for every instance of j, we're going through all of the inputs. As we're going through the inputs, it's going to take output of I, so whichever, essentially iterating through all the outputs, adding input of j, so every single one of the inputs, times the weight of that location, so the weight of the ij location. Since we just filled weights above, it's going to have the weights of all of those items. So it'll set up the output, and I wrote it here, by adding input times the weight to the newly refreshed output. Finally, we go down here, and output of I, so each one of the locations in I, we do more math again. We float cast to using tan h, and essentially setting it to itself after running it through the math function tan h. So it'll be equal to outputs.i, but after it's been run through tan h. Finally, we return that output so that the information is sent outward of the method. The next one is just tan hder, which is a method we wrote just to get the value. It's passed a float called value. We square that and subtract 1, and I needed to do this math, and the easiest way to do it, other than find a function and have to write this into every single area that I needed it done, I just made my own short method for it so that I can call tan hdr instead of having to have the math done in the line of code itself. It just allowed me to get that out and keep the code from getting too cluttered. So the next part is public void backprop output. So this is doing the output for the backprops, so or backpropagation. So it's passed an array of floats for the expected values, and then we move right into a for loop. Again, this for loop goes through every single output and sets the error equal to the output of I minus the expected of I. So it has what is expected and what was actually output, and that's what the error is set to, because error is what was expected to come out minus what actually came out. There's your error. So then we go down into the next for loop, which again iterates through all of the number of outputs, and this one's nested because it's going through weights delta, which is a 2D array. So it goes through outputs and inputs, which are the two contents of weights delta, and sets it equal to the gamma of I times the input of j. So essentially it's taking the gamma, multiplying it by whatever input was in that location, and setting weights delta equal to that number in each of its spots throughout the 2D array. So kind of like the actual weights array, but instead it's gamma times input instead of what was mentioned earlier in the weight setting variable, or method, pardon me. The next method that I wrote was the backprop hidden, because we needed the hidden layer to be in here, which that took a lot of noodling. Again, this was very complex, and I'm sure there are errors in here. But backprop hidden takes in two things. It takes in an array of floats called gamma forward and an array of floats called weights forward. So the first thing it does is starts a big old for loop, and before nesting, it goes through all of the number of outputs, setting the gamma of I equal to 0. So it's essentially resetting the gamma every time it backprops through the hidden layer. And then we get into the nested for loop, which is going through gamma forward.length. So we are checking this new passed in array. We're going through and checking for all variables of j that are equal to or up to the length of gamma forward. Inside of that, we're setting gamma, which we just recently reset, each of the variables to plus or minus, or plus gamma forward of j. So we're taking the gamma forward in that location times weight forward of j and I, which is again passed through up here as a variable, the 2D array. So we're setting each location of I equal to the gamma forward times the weights forward of the locations of I and j based on the nested for loop. Finally, we pop out of there and set gamma of I times equals tan hdir, which is the method I wrote above to keep all of the math out of this actual area. So it's going to take this output, square it, multiplying it by itself, and subtract 1. So it's going to set gamma of I times equals whatever that number is based on the output that's passed into tan hdir. Finally, we're getting into another nested for loop, going through the inputs and outputs, which means that we're handling weights. So this time it's weights delta instead of regular weights, and it's taking each area of weights delta, each one of the locations inside of that 2D array, and setting it equal to the gamma of I times the inputs of j. So it's updating all positions within weights delta to the augmented gamma after it was reset up here and worked through here. So it's multiplying our final gamma by whatever the input is to get that back propagation weight. So that handles back propagation on the hidden layer, and the last thing in here is the updates weight method. So, pardon me. What this does is it goes through, again, a for loop that iterates through every single one of the outputs, and a nested for loop that goes through all of the inputs to update each and every single one of the weights or the positions in the 2D array of weights to minus equal weights delta I of j times a flat value of 0.033. This number was a little randomly made up. I started off with 0.0033, but I saw more issues with that than when I removed a 0. But to get to this, I pretty much just played with numbers less than 1. Honestly, less than 0.5. But it took a lot of noodling, and I'm not 100% sure why this number works so well, more so that it does. And that's a long and confusing neural network code. So none of this actually runs the code that you saw in Unity. That's why I had to write a third script called tester. And what tester does is it trains that neural network, or that multi-layer feed forward. It trains An, which is what we've decided to call it. It will train An. So the first thing it does is it takes in a bunch of public variables, an array of images, which are the buttons, the final result, which is when it displays light or dark, the final text that displays light or dark, what the task values are, and then the call to my neural network code with a variable net. So in start, we have that same list here of this. I kept finding this when I was researching neural networking and all that, so I decided to continue using these numbers. And then it has it sets each of the test values equal to 4, or test values, which is an array of integers equal to 4, so it knows we have 4 test values. And then from net, it runs this with an integer that requires 4 things. We get down here, and this is where we do the training for our neural network code to understand the light or dark. So this time I have it training 5,000 times because I was testing the length of its training. With the other one, I only ran 1,000, but I wanted to see how many I could run to keep training it. And I decided to stop on 5,000 for the sake of processing. So as per with the other thing, we have all of the everything written down here where it feeds forward and back propagates through it, and it'll run these 5,000 times to help train the neural network code. All of this was in here. This was just me doing testing before I got this working. I printed everything out to debug.log. I was checking it in the console just to get the numbers. But when I moved onto the 16 numbers, I decided not to keep working with this, but I left it in just for safety. I also blocked out update because I never really used the update method, so I didn't find it worthy. But I wanted to keep it in there anyway because I just don't like deleting things if I don't have to. Now, next up was the change color, which we saw before in the perceptron. This is just where if you click one of the buttons that is white, it'll change black. If you click a button that is black, it'll change to white. This is just to help us set up our test cases so we can run different tests based on what colors the nodes are. And then this is where it actually runs the test, as you can see by the name run the test. So it takes the float is bright result or is dark result, and then runs it through the net feed forward both times, testing each of the test values, so 0, 1, 2, and 3, which are each of the pardon me, each of the blocks, the dark and light blocks, and then it checks if it is dark or if it is bright based on these integers 0 and 1, what the expected result is. Then it'll go through and it reaches to the neural network code for most of these things using net.feedforward and net.backprop. But it'll go through and it check if the brightness result is greater than the darkness result, then the color is bright and the cube will change yellow. If the color, otherwise the color is black, so it'll change to a black cube and the color is darkness. And that wraps up all of the code. So this is the training. This is where all the code is implemented for the neural network, for the AN, and this is where the perceptron, all of the code has been created for here. So to run it through one more time, this is the test of the neural network, or the AN. So I have to start the program. It'll launch. It's doing the 5,000 calculations, which again, I left it at 5,000 because that loading process takes a lot longer the more you have. So you can click on things, change their color, and it'll tell you if it's dark or bright or not. So, and then one more look at the perceptron. And again, same thing, you let it load. It does the 1,000, runs through the 1,000 times to train the perceptron, and then you set default weight, and it'll tell you if it's dark or bright or not. And then you can set random weights, and it'll do the same thing, where it tells you predominantly dark or white. So this code was very, very complex, and one of the harder things I've had to learn in a while in regards to programming. So I'm hoping that the results I produced are acceptable. Otherwise, thank you so much, Professor. Again, this has been Harrison Hopkins with Assignment 3 in AI. Bye-bye.